Okay, so in this video, we're going to cover section 3.1, which is on quadratic functions. This is something we've seen already, but we're going to further analyze quadratic functions or quadratic polynomials and learn how to draw or sketch graphs of quadratic functions, given some minimal information about the quadratic function, in the sense that minimal in the sense that rather than taking in a given quadratic function and making a table of values and then plotting it, there's really only a few pieces of information, 2 or 3 perhaps, that we need in order to get a reasonably good sketch of a quadratic function. Let me share my screen now. Okay, so as I said, this is section 3.1. And this is on quadratic functions. So first, let's recall what a polynomial function is. So a polynomial function is a function of the following form. So we have these coefficients, these x terms to various powers. So we have a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 power. And then we have some intermediate terms. And then finally we have a1x plus a naught. And the coefficients are real numbers, so a0 up to an are real numbers, and then we have n is some fixed positive integer or some natural number. So an is, which is non-zero, is the leading coefficient. And a naught is the constant term. These are just this is just terminology. So a sub n is a non-zero coefficient. It's called the leading coefficient. And a sub 0 is called the constant term. So we've already studied, so also I should actually say, this number right here is called the degree of the polynomial. It's called the degree of the polynomial. It's an n-degree polynomial. So that is, i.e., p of x is an n-degree polynomial. So we've already looked at second-degree polynomials or quadratic polynomials in some depth, but what we've really studied in depth are 0-degree and 1-degree polynomials. So 0 and, I should say, maybe I'll just write it out, 0 and 1-degree polynomials. We've looked at these quite extensively already. So these are polynomials of the form p of x. So if n is 0, that means the only coefficient we have is a sub 0. So it's just constant. or if n is 1, so 1-degree polynomial, it's something of the form a1x plus a0. And these are both lines. These are the graphs of these polynomials, or these functions, correspond to lines. This is a horizontal line. And this is, so assuming a1 is not 0, this other, the graph of this polynomial is some line with a slope. It's not horizontal, it's angled somehow. In this section, we want to look at quadratic functions, though. We want to look at these ones in further depth. So a quadratic function is a second-degree polynomial function of the form sorry, my pen's acting up for some reason. So it's something of the following form, where A, B, C, let me put it on the next line actually. So A, B, and C are real numbers. And A is not 0. Otherwise, it just, if A were 0, it would just reduce back to the 0 or 1-degree polynomial case, which we already know how to handle. So the one particular type of quadratic equation we've looked at really in depth and is we've used as a lot of to illustrate a lot of concepts is the one corresponding to the parabola. So that's when you have A is equal to 1 and B equals C equals 0. So that in this case, f of x is simply x squared. And the graph corresponding to that is something like, we've seen many times, it's a parabola that opens up at the origin like this. And we've used this to illustrate a lot of concepts. For example, symmetry of graphs, symmetry of functions. We've used this to illustrate those concepts and various other concepts. But we want to go beyond that further. We want to look at something more generally. So we want to look at a more general quadratic equation, which may not satisfy this at all. B and C might not be 0, A might not be 1. And we want to know, how do we plot these functions more easily? Well, it turns out that we can always express we have this fact: any second-degree polynomial function can be expressed in so-called standard form. With this nice fact right here. And standard form is this. It's simply this. So you have coefficient A, and then you have x minus h squared plus k for some h and k real numbers. You don't know maybe what they are all the time. You can actually determine what they are in general, but it doesn't matter. Just that the point of standard form is that there exists h and k such that f of x equals this. And how do you put f of x in this form? Well, you complete the square. That's the proof. So the claim is that any polynomial can be expressed in this form that I boxed right here, and the proof is you complete the square. But it turns out that in this form, this will tell us everything we need to know about the graph of f of x. We don't need to plug in points and build a table and then plot them. make a plot according to the table. We just need to put the function in standard form. So let me explain some of these features of this function. So the first is that the graph, the first is that these numbers h and k, they form an order paired. Sorry. H and k form an ordered pair, a point in the plane, and this is the vertex of the graph of f of x. So this piece, the h and k give us the point at which that parabola opens up, in a sense. So when, let's just go back to our standard example. When f of x is this implies that, well, first of all, f of x can be written, if you start with this example, it can be written as 1 times x minus 0 squared plus 0, right? This is valid. This is a true, this right here, this equality holds. This is, I've just rewritten it. You can, x minus 0 is just x, and then that's x squared. Then 1 times x squared is just x squared. And when you add 0 at the end over here, it doesn't change anything. So you do this, in fact, equation in fact holds. But in this form, it tells you that h is 0 and k is 0. So the function should open up at the point 0, 0. And in fact, it does. If you plot f of x squared, it opens up. Let me just bring it. I drew the plot right here. The vertex is at the origin right here. So it opens up at the origin, just as the theorem predicts. And as I said, so the claim is that any second degree polynomial can be expressed in so-called standard form, and the proof is complete the square. And that's in fact how we're gonna, when we're gonna be given a polynomial, and we're gonna be asked to put it in standard form, and that's exactly what we're gonna do. We're gonna put it in standard form the questions will ask us to put in standard form, and we'll do that by completing the square. So let me put a bullet point here. So this is the first fact or feature of this equation that we can is helpful in determining the plot. The next one is the sign of the coefficient a. So we have these two cases. If a is positive, then our graph might look like something. So this corresponds to something like the following. So maybe the point HK is right here, and it's going to open up. So this point is the vertex HK, and the fact that A is a positive number means that the graph is going to open up at the vertex HK. And then the next case is under this bullet point is when A is 0, and as you can guess, it's going to show the opposite behavior. And so say the point HK is about here, it's going to open up downwards like this at HK. So let's look at an example of putting determining information about a function from standard form. So this is example 1, and from this from standard form we can deduce a lot actually. So we're given the following function: 2x squared minus 12x plus 13, and we want to put this in standard form So the first thing is put this in standard form, then find the vertex, x and y intercepts, sketch it, and then state the domain and range. Well, the domain is really easy because the domain is the largest set, or the largest set of values for which the function is defined, for which it makes sense. So f is gonna, we can start with that. Well, that's a pretty easy question to knock out. The function is a function from R to R. Now, the range, it won't be all of R. So in other words, the codomain and the range and the codomain are not going to be equal, but the domain right here is definitely going to be all of R. We can plug in any real number to the function. So let's start now that we've answered the domain question. We'll get to the range question later on. Let's look at putting this in standard form. So the first step is to factor out a 2. So this is basically like, I mean, this is literally completing the square, which we've done already. We've done completing the square to just put quadratic equations in a certain form, which we've done already, yeah. And then also completing the square for equations. So this is going to look very familiar, but I just want to go through it just because it's been a little while since we've done this. Last time we did completing a square was for circles, and that's slightly different. So the first step, though, is to factor out the 2. So we have x squared minus 6x plus 13 over 2. And then we want to do that completing the square business right here. And we want to do completing the square, which involves looking at this coefficient and then factoring this whole thing at the end. So if you recall, you have the coefficient of the middle term. So that will be -3, and then you square it. But then we need to subtract that off because we don't want to change the function in any way. And then we have to tack on this constant right here. So this goes here. This should be a 2. So right here, we can factor this now, this part right here. So I'm going to put a square bracket right here. I need another bracket. So this is going to be x minus 3 squared. And then we have to combine these terms. So this will be -3 squared is 9, but then it just becomes -9 because we have that negative on the outside. 2. Oh, this should be a square bracket right here. And then we get this. And this will be 18 over 2. So this will be, I guess, 5 over 2, maybe. Let's see. Yes, okay. And then now we'll distribute the 2 back through. So we get 2x minus 3 squared, and this 2 cancels with this 2 right here, and we get -5. And so in this case, a is equal to 2, which is positive, and h comma k is equal to 3 minus 5. So this will give us, this tells us that the parabola opens up at this point right here. So the next step is to find the x and y intercept. So the x-intercept is found by setting the function equal to 0. So we set 2x minus 3 squared minus 5 equal to 0. And then we can add 5 to both sides and divide by 2. So we get this 5 over 2, and then we can take the square root. And we get, root 5 over 2, or plus or minus. And then we can add 3 to both sides to get this. And I'm not going to give you, I don't think I'd ever sign a problem with horrible numbers like this, but because they're going to require a calculator to get an idea of what their magnitude. But if you calculate these numbers, you find that the x is approximately 1.42 and x is approximately 4.58. So these are the x-intercepts. The y-intercept is found by plugging zero in for x. And that will give us, and simplifying, that will give us the y-intercept. So I plug in 0, we'll have 2 times 0 minus 3 minus squared minus 5. And we can simplify that. So this will be 9, or sorry, so negative 3 squared is 9 times 2 is 18 minus 5, and this will be 13. So the y-intercept is 13. And now we can actually sketch, we can give a rough sketch of this. So if we collect all this information, so what we have is our graph looks something like this. I'm not going to be precise here. You can go in the book if you want a more precise, see a more precise plot. The idea is we have the vertex here, so this is -3 or 3, -5. It opens up like this, and then it opens up like this. So this number right here is approximately 1.42 for the one x-intercept. This one right here is approximately 4.58 for the other x-intercept, and this number right here is exactly 13. So the plot is going to look like this. And of course, if you're doing it by hand on paper and a pencil, you could probably do a better job. But we can get a good, just from the standard form, we can gather a lot of information. And finally, we want to know the range. So the function, or if you recall, the function in standard form is this. So this is always, so you can see from the graph, if you like project the graph onto the y-axis, so this point is, project the vertex, you'll get here. So this is going to be -5, but then anything above -5, if you take any point on the y-axis that's above -5, you'll find a corresponding point on the graph itself. Right here projects over here, but it also projects, over here if you extend this graph up. So what that means is that every point on the y-axis above -5 corresponds to a point on the plot. So that this whole, this whole line right here is the range. And that can also be seen algebraically if this number is positive. So because this number is positive, this overall thing, this is a non-negative number always. This means that this will always be greater than or equal to -5, right? If you took this number away, if you just ignored this, the smallest this can get is -5. And then if this is some non-zero positive number, it's just going to make this overall number bigger than -5. So from the plot, we can deduce what the range is, but from the function in standard form, we can also deduce the range, or what I call the image. And we can see that the image is -5 to infinity. So the last thing I want to talk about is the maximum or minimum value of parabola. It turns out that a parabola or quadratic function can only have one of two. It can't have more than one. It can't have both a minimum and a maximum. So you probably can gather what this already is referring to. The maximum and our minimum will be determined from the standard form. So we're going to start with a function in quadratic form. I'm sorry, we're going to start with a quadratic function in standard form. So it'll be of this form. And the claim is that the maximum or minimum value of f occurs at x is equal to h. So what this means is that the point h, f of h, is a minimum or a maximum point. But if you plug in h, it's clear that if you plug in h into this thing right here, h minus h is 0, so f of h is equal to k. So that means that the vertex is where a max or minimum point is going to occur. And that makes sense from the plots that we've looked at already. And we're going to basically have two cases. We're going to have the first case, so a minimum or maximum is guaranteed to occur at the vertex. But the question is, well, what do I know? How do I know whether it's a minimum or a maximum? And that will come about by looking at that coefficient a. So you have two cases. If a is positive, then f of h, which is equal to k, is a minimum value. And the other case, the only other possible case, is a is negative, and that's that implies that f of h, which we just determined is equal to k, is I'm sorry, I got this backwards. No, I didn't actually. When a is negative, that implies that k, f of h is equal to k, is a maximum value of the function. So let's just illustrate this with a graph and we'll call it a day. So these two cases, so we have this case, so right here is h comma k, and this is when a is greater than or equal to 0. And then we have this other case. Oops. Oops. So, anyways. So this is right here, HK, the vertex is HK, and then this corresponds to is less than 0. So, as I said, a minimum or maximum, there is always a quadratic function always has a minimum or a maximum, and the minimum value or the maximum value occurs at f of h is equal to k. But that doesn't tell you whether, so we call these actually extrema. These points, these are extrema. So an extrema is guaranteed to exist, but we don't know whether that extrema is a minimum or a maximum. That's where looking at the coefficient a comes into place. If you have that a is positive, then that extrema is a minimum value. If a is negative, this extrema right here is a max value. So I'm going to stop here, and then this will conclude section 3.1.